All right, from current slide. Okay, any questions on anything we've done so far? Now, I'll apologize ahead of time. I thought I had one of those deadlines that I was telling Matt about that was for this coming Friday. I thought it was last Friday. So I didn't take either book with me because I thought I'd be working all day on that. When my boss finally came in, I said, "No, these are due today." He said, "Oh no, we can wait till next Friday." I went, you know. And then since then he's come out with something. I need something on Tuesday, which is even worse. Okay, so anyway, it's just that point of the term where lots of things. Oh yeah, the other thing I was thinking of, that deadline's already passed, but I'm trying to catch up and meet the deadline. That was the first of the month, and still trying to get that completed. Have well on the way, but not complete. So anyway, things are just crazy right now. And they just about always are. So, okay. We were talking last hour. Any questions on anything we covered so far? But I guess I interrupted myself several times there. I don't have your, what you want to call it? Yeah, your test made out yet. I have part of it done, but not all of it. So I've got to do that. And I would say I would do it this afternoon as soon as this class is over with. Normally I'd say that, except I got the deadline for tomorrow that I have to get moving on that. I don't think there's any way I can get it all done by tomorrow, but at least I want to be moving in that direction. Okay. Any questions there? All right, where we left off last time was on page 37, example 2. And that was direction fields, okay? And actually what I'll do is back up one and use this graph here. It says use a direction field to sketch an approximate solution curve for the initial value problem. Oops, let me get my pen. Where is it? There it is. Activated. Okay. dy dx is equal to sine y. Okay, when y of 0 is equal to negative 3/2. Okay. All right. Need a few points here. dy dx is sine y. Okay. Now, this one only has dependence on y. So the x's can be anything. So give me a point. Any point. 3, 2. Oh, he goes for weird ones. Here's 3 and 2. Right there he is at 3, 2. Not much of a point, but I didn't want to make it too big there. Okay. Now at 3, 2, at that point 3, 2, what is your dy dx? And let's just make life a little easier. Give y's in terms of pi's. Does that make sense? Okay. So give me another one. Say again? Pi over 2. You want 3 pi over 2? Is that what you want? Yeah. Okay. 3 would be here for x. Pi over 2. Now remember, pi over 2 is about 1.57. Because pi is 3.14, right? So pi over 2 would be, I think, pi divided by 2, 1.5. A little over 1.5, right? 1.57. Okay, 1.57. So that would be 3, 1.57. So I'm going to put it right there. Not far from what you said, but a little bit off. Okay. and you said pi over 2. So sine of pi over 2 is what? One. Yeah. Sine of pi halves is 1. Okay? So this will have a slope of 1. That's about like that. Okay? Agreed? Okay? Give me another point. I don't care what the x is, but make the y's in terms of pi's or half pi's. Give me another point. 0, 1, or 0 pi, 0 pi halves. You choose. Just make it. Okay, what you want? 0 pi halves. So 0 pi halves, the y will be pi halves again, which is about here, and that also has a slope of 1, right? Give me another point. In fact, anywhere at pi halves, you have a slope of 1. So all these are going to be slopes of 1. Every one of these is going to be a slope of 1. See what I'm doing? Doesn't matter what the x is, the dy dx is slopes of 1. I'm not very uniform here. Ah. How they, some of them disappear. Okay. Give me another. Okay, there's all the x's that I'm going to draw with slopes of pi halves. So the y's are pi halves. Give me another xy pair. Only the y can't be pi halves. Anyone? Y'all work way too hard. How about 0, 0? Is that okay? Okay, what's the sine of 0? Sine of 0. Cosine of 0 is 1. Sine of 0 is 0. Okay? So everywhere that y is 0, you have a 0 slope. So I'll draw all these in. Doesn't matter what the x is, these are all 0 slopes here. Do you buy this? I guess they could be pointing in the other direction, but I'll just make them positive zeros, whatever that is. Okay, 0 slopes there. Okay. Give me another xy pair. 0 pi. Okay. So x is 0 pi. Okay. What is the slope there? 0 again. So pi is 3.14. So here we'll have all zeros here too. Actually, I sort of feel like I ought to put the zeros in the other direction here, but this will be fine. I guess I could have done one like this here. All 0 slope. Oh, whoa, whoa, whoa. Drew these too low. It's 3.14, which I'm not sure I'm at 3.14, but somewhere there. These are all 0 slopes here too. Okay, give me another one. Yes, absolutely. Okay, let's just think about that a minute. At any x, when y's are minus pi halves, what is the sign of negative pi halves? Say again? Negative 1, okay? So down here at 1.57, they'll be at negative 1. That's not a very good negative 1, okay? You get the idea here. Okay. Oops, I'm drawing some of them too long. But these are just pointing in directions. The magnitudes are not really all that important here. Okay? And at negative pi, you're going to be 0 again, the negative 3.14, so, ooh, that's probably too much. Okay. A lot. Okay, 0, 0 we've gotten already. Y equal, we did 0, pi halves, pi 3 halves pi. Y is equal to 3 halves pi. What is sine of 3 halves pi? Nope. Negative 1. Okay. 3 halves pi would be about 4.5, a little beyond that, maybe 4.6 or so. Maybe a little bit more than that. So 4, 1, 2, 3, 4. Somewhere up here we'd have a negative 1. All these are negative 1s. But you know we really don't need all these, do we? We just need the one where y of 0 is equal to negative 3 halves. Okay? Y at 0 is equal to negative 3 halves. Negative 3 halves would be somewhere right about here. So it's going to be a curve. Okay? At just past here, it starts going up again, right? Here it's 0, negative 1/2, 0, and just barely going positive again. Okay? So here it's just barely going positive. Okay? And flattens out here a little bit. And it looks like to me it's a curve that's going to be doing they don't show this one. I don't think they do. Is it on the next page? Yeah, there it is. Okay. They show a lot more lines than we do. Okay. Oh, wait. It's negative 3 halves, not 3.5. I thought mine looks rather weird. Okay. I'm sorry. I misread. Misstated. That's negative 1.5. Yeah. Okay. Negative 1.5. That's right here. Right about here. Just above where that one is. So it's going down almost in this direction here. And it seems like it goes along here and then heads in that direction. And from here, it must have come something like this. So it's a curve that's sort of like that. And sure enough, that's what they've got. Okay, sorry about that. I looked at the wrong one. There's the curve. It kind of goes like this. It almost looks a little bit like a sideways tangent curve, but it's really not, I don't think. But it has to be going along something about that manner. Okay? There's infinite number of curves you could fill in here that you see up here. The curves would be doing something like this. You know, it just depends on where you're starting from and going to. You know, Up here, they could have been going, like this, and there's an infinite number of curves. Just pick any and do along there, You can have any ones that mirror this and, go like this, or like this, or like this, or like that, or come down like this, or another group that goes up like this, infinite number, but we want the one that goes through 0, 3 halves, because y of 0 is 3 halves. So pick that curve and then let it continue like that. Does that make sense? Okay. All right. Now, there's another little blurb here. After that example, before you get the figure of it, it's increasing, decreasing. Interpretation of the derivative dy dx as a function that gives slope plays a key role in the construction of the directional field. Another property of the first derivative will be used in next, namely, if dy dx is positive, greater than 0, or dy dx is less than 0, for all x's in an interval I, then the differential function y of x is either increasing or decreasing on I. And that's on the interval I. Then they have a little remark here, and sketching the directional field by hand is straightforward but very time-consuming, as you just saw. It is probably one of those tasks about which an argument can be made for doing once or twice in a lifetime, but overall most efficiently carried on by means of computer software. So do a few just to get an idea for them, but most of the time you're going to do it. Before calculators, PCs and software use the method of isoclines to facilitate sketching direction field by hand. For a differential equation, dy dx is equal to f of xy. Any member of the family of curves, f of xy equals c, where c is a constant, is called an isocline. Linear elements drawn through points on specific isoclines, say f of xy equals c1, all have the same slope, c1. So blah, blah, blah. Now, another more specific definition for an isocline is an area of equal elevation. Okay? So if you have a topographic map and you see these curved lines, everywhere on that line you're at constant elevation. You're not going uphill or downhill, but you're following the curve. Now, if you're in a place with a lot of ravines, you may go around the edge of the ravine like this, but you don't go down and up again. So we had an Italian kid that lived with us one year. His folks were friends of ours, and he was born in the U.S., the kid was, so he was eligible to go to college either in the U.S. or in Italy. And his father wanted him to have the opportunity to choose, so he wanted him to come to high school in the U.S. for at least a year. So he came his senior year and lived with us and graduated from the U.S. high school. He was a really bright kid. But he ran, his sport of his choosing was, goodness gracious, blank on the name, orientation. Have y'all ever heard of it? Orienteering. Orienteering. And what that is, someone has laid out a course out in the woods somewhere. Usually it's in the woods. It could be in the city. It could be anywhere. And they set up stations. And all you have is a topographic map of that area with the stations identified where they are and a compass. And you take off and start running. Okay? You know where you're beginning, and you have to hit the stations in a given order. You choose your pathway. And he actually did his science project, in the science fair that goes around on orienteering, because that's where his interest was. And we had a two-variable thing about whether he should choose the path of shortest distance, which would be lots of elevation changes, or least elevation changes, which would be a longer path. And we what we did, we would have Saturday after Saturday after Saturday at one place they had set up in Red Mountain State Park. They had run an orientation thing, so he asked them to leave it up for him so he could go out and run several things. He first run as close as he could to minimal elevation changes, and then he'd run the next time he'd run it minimum distance changes, and then he set up a formula, and tried to model how he could calculate the maximum. And my word, it was a pretty, he did a lot of work on it, but it was sort of not one of these, we're finding the enzymes that are going to cure cancers or something like that, It was a pretty simple type thing, but really he did it pretty well, and it had statistics in it and stuff. And the judges just really liked it, not as much as the big fancy ones. He kept coming in third in every level, okay? And so he kept going to the next one until finally when he reached the state level, he came in third again, but they only took the top two, the nationals, in the local, in the regional, and everything. He kept coming in third. They took the top three. And then finally when he got to the state level, sure enough, he beat all these other ones and twos, but he came in third. So he didn't have the opportunity to go anywhere, but he was tired of it. We were tired of it, but yeah. But that's an isocline, a line of equal elevation. In weather mapping, isobars, areas of equal barometric pressure. When you have a very strong high pressure center, you'll see these circles come together and the numbers are increasing. Or low pressure, which causes weather like we have today, those circles would be going smaller things. Look just like isoclines on a topographic map, but they're isobars on a weather map. And then you can have isotherms, equal regions of equal temperature. You could have an iso anything. So when they say isocline here, it has one meaning, but it's also it technically is equal elevation. It's isocline. Why did I get off on that? I'm not sure. Okay, let's go to 2.1.2. Autonomous first-order differential equation. I always try to mispronounce that. Autonomous first-order differential equations. What in the world is this? In section 1.1, we divided the class of ordinary differential equations into two types: linear, nonlinear. Ordinary differential equation, linear, nonlinear. Now we'll consider briefly another kind of classification of ordinary differential equations. Classification is of particular importance in qualitative investigation of differential equations. An ordinary differential equation in which the independent variable does not appear explicitly is said to be autonomous. If the symbol X denotes the independent variable, then the autonomous first-order differential equation can be written this way. Let's go back to the other page, and it would be f of y, y prime, first-order ordinary differential equation. This would be equal to 0. Okay? Okay? In other words, there is no x dependence. Okay? Or in normal form, this would be dy dx, which would be your y prime, is equal to f of y alone. No x dependence. Okay? We shall assume throughout the function here, f of y, the f function here, and its derivative, f prime, are continuous functions on y on some interval I. So the first order differential equations, dy dx, is equal to 1 plus y squared. That would be autonomous ordinary differential equation. Dy dx equal to 0.2xy, would that be an autonomous equation? No, because there's x dependence. This one is fine. 1 plus y squared, there's no x dependence. That one would not be a autonomous. So this is called a non-autonomous ordinary differential equation. Many differential equations encountered in applications are equations that are models of physical laws that do not change over time are autonomous. That's when your independent variable is time, not displacement, okay? As we've already seen in 1.3, in an applied context, symbols other than y and x are routinely used to represent dependent and independent variables. For example, t, that could be it. So here's one you'll see quite a bit. dA dt is equal to Ka. Okay? Now, that could be a whole bunch of things. Here's one thing it could be. The rate of change of infections is proportional to the number of infections you have. That makes sense, doesn't it, in a medical sense? If no one's sick, then you're not going to have any, rate of change of infections because no one's infected. But if one person's infected, then that one person is only going to interact with just a small number of people, so the rate of change is going to be pretty small. But if the number of people already infected is pretty high, then the rate of change is going to be pretty high too, because they're influencing a lot of people, okay? So that would be one example. Population growth, I mean, lots of things, yeah. The rate at which a population is expanding is directly proportional to what that population is, okay? Because if you only have a couple of, say, couples of an almost extinct species out there, the rate at which that species is going to increase is going to be pretty slow because you're down to just the fertility rate of a couple of pairs, okay? But if you have a huge population, boy, it can take off and go really big, okay? Here's another one. Dx dt is equal to kx times n plus 1 minus x. Now, I can't right now think of anything that would be particularly, but it's something that the rate of change of your dependent variable depends not on the independent variable, but only on the dependent variable. So this is a quadratic dependence of minus x squared, okay, if k is positive, and then plus a kx in there, where n is some counter or something. So that would be some sort of a quadratic dependence, okay? I can't think of what that would be, but I'm sure there are examples of that. Here's one, almost the symbology gives it away, dt dt. Okay, what does a capital T usually stand for? Physics majors, huh? Temperature, okay? Usually absolute, but not always, but usually absolute. What's that? And small t is top, usually, okay? It could be any parameter, but is equal to some constant times T minus Tm. Now you could use the suffix anything you want to. I usually am used to seeing it as T0 or TA or something like that. And this is the rate of change of temperature is proportional to or equal to K times the difference of T with the ambient temperature. And that makes sense, doesn't it? If the object in question is extraordinarily hot, then its rate of change is going to be pretty rapid because this is a great deal larger than your ambient temperature. But if you're really close to the ambient temperature, the rate of change is going to slow to almost a crawl, okay? Or if the temperature of the object is actually less than the ambient temperature, it's going to slowly come up to it, unless it's way less to it, and then it's going to come up pretty rapidly to it. So yeah, that's Newton's law of cooling or heating, okay, is generally what that is. And here's another one, dA dt, okay, is equal to, this is pretty specific, 6 minus 1 over 100 A. Now, I can't imagine exactly what that would be. But it could be some physical quantity. I don't know what it would be. Now, so all those are autonomous because you don't see any little t dependence on any of those equations. You do see an x dependence here that's not autonomous. This one is autonomous. That's autonomous. That's autonomous. Okay. Now, the zeros of a function f in this first form right here, this is the form they keep referring back to. The zeros of that function are of special importance. We say that a real number c is a critical point. You have heard that before. Okay, a critical point of the autonomous differential equation 2 if it is a zero of f. That is, if f of c is equal to 0. Now, that's not exactly what we talked about critical points before. Usually we're talking about f prime of c is equal to 0. That would make it a critical point, but this is f of c. But it could just be another class of critical points. A critical point is also called an equilibrium point or a stationary point. Okay? Now observe that if we substitute the constant function y of c into the function up there, f of y, then both sides of the equation are 0. That means if c is a critical point of this equation, f of y up here, then f of y is equal to c is a constant solution of the autonomous differential equation. A constant solution y is equal to c, y of x equals c is called an equilibrium solution. Equilibria are the only constant solutions of that. Okay. As was mentioned, we can tell when a non-constant solution y is equal to y of x, that is increasing or decreasing by determining the algebraic sign of the derivative. In the case of equation 2, we do that by identifying the intervals, on which the y-axis over the function f of y is positive or negative. Okay. So let's do one. Example 3. It sort of seems like a lot of blah, blah, blah at first, but let's see what. Differential equation dp dt is equal to p times a minus bp. Okay. Where a and b are both positive constants. Okay. This has a normal form, okay, going back to the other thing, dp dt is some function of p and p alone. Okay. A and b are constants, so they don't really enter it, but it's a function of the variable p. Okay. But now t is your independent variable. P is the playing the parts of x's and y's before. Wow. I sort of don't like that statement too much because t is playing the part. Oh, I'm sorry. Okay. With t and p playing the parts of x and y respectively. T plays the part of x, p plays the part of y. Okay. Hence it's autonomous. And from the thing that this, of course, this f is equal to that, and then where you set that equal to 0, okay, that's going to be a critical point, okay, And actually that is what we were talking about, because it's the same C critical point we were meaning before, because remember, this dt is a first derivative, and it's the first derivative of this function of p, and where that's equal to 0, that's where your first derivative is 0. So those are your critical points, okay? I was thinking they meant that the f itself, which I didn't know they were meaning the one from that formula above. Okay. So, obviously here, this is a factor of a product of two factors, right? And if that product is going to be 0, that implies that either p is equal to 0, which of course then your derivative would be 0, right? But not just that, or a minus bp is equal to 0. Solve that for p, and that would be a is equal to bp. And solve that for p, p is equal to a over b. That would be another solution, either p equals 0 or p equal a over b. Okay? And this is p of t. This is a function of time, or t, whatever your parameter t is. By putting the critical points on the vertical line, we divide the line into 3 intervals. Okay, now remember, this would be your t-axis, this would be your p-axis, because t is taking the place of x and p is taking the place of y, right? So let's divide that p-axis into various components. When p is equal to 0, there's a critical point there. And then you have 1, 2, 3, 4, blah, blah, blah. Somewhere here is the point a over b. Okay? Now, okay. You know, p is equal to 0 here, p is equal to a over b there. Now, because those are your critical points, we know that the function p is either here at 0, p is equal to 0 there, or your rate of change is 0 there, that's your critical point. So either it's increasing after this and decreasing here, and then increasing here, or you have what you need to do is that splits the range up here into, this range is the best word for it, into 3 areas. 0's here and here. It's either all positive here, all negative here, all positive here, all negative here, all positive here, all negative here, or something like that. It fixes that this cannot have a sign change in between, because for it to be a continuous function as derivative of a continuous function, you can't have a sign change in here without another 0, okay? Because it's a continuous function. So you can't go from positive to negative. It can here or here. Even then it doesn't have to, but at least it gives you a clue, okay? And by the way, we said a and b are both positive constants, so therefore the a over b is positive, okay? Remember, up here we said a and b are both positive constants, so the ratio of a to b is positive. It may be very small, but it is positive, or it could be quite big. Okay. Okay, let's move on. I think that's all there was to that one. Figure 2.1.5, and that's, oh, I've already drawn that one here. I was starting to look for it on my DVD, and I don't have a DVD, no PowerPoints here. This figure here, this one here, this drawing here, is called a one-dimensional phase portrait, or simply a phase portrait of the differential equations, and that shows, and that's the phase line. It indicates where the function is going. And again, these are the two zeros, so it's either plus, or minus, plus, or minus, because you have a change here. Unless, of course, that happened to come down and kiss the axis there, but not intersect, okay, and not cross. In that case, you could have a plus on both sides of it. Okay. But we'll worry about that later. Okay. They drew it as if it's decreasing on top, increasing in between, and decreasing below. Okay. So without solving an autonomous differential equation, we can usually say a great deal about its solution curves, since the function f in this kind of a thing here, expression here, sorry, is independent of the variable, in this case p, t, in this case t, independent of that variable t. Okay. We may consider f defined for minus infinity to x to positive infinity, or for the interval of the y-axis. This is sort of a lot of verbiage here. So let's say, for the sake of discussion, let's suppose that this equation has exactly two critical points, C1 and C2. C1 less than C2. So we'll call this C1, this C2. Exactly two critical points. The graphs of the equilibrium solution y of x, or this case p of t, goodness gracious, is equal to C1 and is equal to C2, as long as C1 is less than C2. The graphs of the equilibrium solution y of x is equal to C1 and y of x equals C2 are horizontal lines. Horizontal lines. And these lines partition the region R into three subregions, R1, R2, and R3. That's what I was sort of calling this, R1, R2, R3, if you had two critical points. If you had three, you got four regions, one more than you always have. Okay. Without proof, here are some conclusions we can draw about the non-constant solutions y of x, or p of t, in such an equation such as that. All right. Here's a conclusion. If x0, y0 is in a subregion of this, let's say it's here, x0, y0, okay, is in a subregion of Ri, this happens to be R2 here, and y of x is a solution whose graph passes through that point, xy, x0, y0. Okay. Okay, I'm getting lost in where this is. 2 critical points, okay. The graphs of the equilibrium solutions, y of x equals c1 and y of x equals c2, are horizontal lines, okay? Maybe I should do this in a different color. What color would you like it? Yellow? Okay, I hope you'll be able to see it. Not very well, but it's there. Okay. Now, with these lines partitioned in the 3 subregions, without proof, here are some conclusions you can draw. Okay. If x0, y0 is in a subregion, yeah, we already said this one. What they're getting at here, just looking, what if the, let me go back to something, I'm going to choose blue now to match what they've got. Let's say the curve is doing something like this, okay? If it's moving in that direction, it can't cross this and it can't cross that. So it's going to basically continue in some fashion such as that. If, on the other hand, it had been going the other way, let's say green, then it would have been going like this and like that, you know, if it was going the other way. I think that's what they're getting at here. By continuity of f, we must have either f of y is greater than 0, f of y is less than 0 for all the x's in the subregion Ri. In other words, f of xy cannot change signs in a subregion. It would have to change only in the bigger regions like we have there. Okay. Since dy dx is equal to f of xy, f of y is a function of x, is either positive or negative in the subregion, then a solution y of x is strictly monotonic. And that's sort of what I was showing here. Here it would be strictly decreasing, here it would be strictly increasing. It can't really back up on itself and fit all the other requirements that we have for it. So, if y of x is bounded above by a critical point, C1, for all x's, then the graph of y of x must approach the graph of the equilibrium solution as is. Okay. All right, I'm not really. Okay, if y of x is bounded above by a critical point 1, C1, okay, then the graph of y of x must approach the graph of the equilibrium solution y1 is y of x equals C1 is either x approaches positive infinity or negative infinity. if y of x is bounded, that is bounded above and below by 2 consecutive critical points, then the graph of y must approach the graphs of the equilibrium positions. If y is bounded below by a critical point, as in the region, then the graph of y of x must approach the graph of the solution y is equal to C2 either trouble focusing my eyes here. It's so dry. And the graph of y must approach the graph of the equilibrium solution as x goes either. Seems like it's saying the same thing the previous one did, but okay. Let's go on to example 4. We're going to look at example 3 again. Okay. Here are our regions. Okay. The C1 is the C1 at 0, C2 at B, A over B. Okay? Now, the 3 intervals determined on the p-axis or phase line by the critical points 0 and A over B now correspond to in the t-plane to 3 subregions defined this way. Let's see, region 1. They did it at the bottom, okay. This is now the region, well, let me change back to black. And also do my eraser, okay. Okay. This is your region. I thought I changed back to black. Okay. Region 1, region 2, and this is region 3 up here. Okay. Region 1 is all negative values for p, less than 0. Region 2 is between 0 and A over B. And region 3 is all values of p greater than A over B. Okay. Now t is going from minus infinity to positive infinity. The phase portrait shown in this figure tells us that p is decreasing P is decreasing in R1. Now, it's just because of their figure here. So here's the deal that we've got. Let's take out the blue curve. I'm just trying to mimic what the book is saying. Okay, and let's see. Guess we'll go back to green. Well, I can't get the pen to come up. There it is. I'm going to go to a darker green though. Okay, this is showing that P is decreasing in region 1 and therefore increasing as shown in region 2 and decreasing again in region 3. Okay. Now, for P0 less than 0, then you have a bound. So any P0 down here, less than 0, there's your C equals C1 equals 0. So for any P value down here in R1, okay, P of T is bounded above, and it's bounded above by this curve y is equal to C1. Okay, so it can approach it, probably will never touch it. Okay, monotonic. increasing toward it. Okay, since P is decreasing, okay, all right. Then for P of T equal to 0, that's a horizontal asymptote for the solution curve. Well, we've already said that. It's the yellow dotted line there. Nigel wanted yellow. Okay. Since, okay, and for any P0 greater than 0 in region 2, but less than A over B, still in region 2, it's bounded, both from above and from below. And since P of T is increasing, we just sort of randomly assumed that, okay? Since it's increasing, I drew one curve here. There's various ones you could do there. Okay. For P greater than A over B, up there in region 3, it's bounded below, and since P of T is decreasing, P is approaching A over B as T approaches infinity. The graph of the equilibrium solution is a horizontal asymptote. The black dotted line. P is equal to C2, which is A over B. There's a horizontal asymptote for both the upper solution curve and the region 3 curve and region 2 curve. All right. Looks like just a lot more blah, blah, blah. Now, in the subregion R1, down here, example 4, where P of T is decreasing and unbounded below, we must necessarily have that P of T is here approaching negative infinity. There's no bound down here. There wasn't another 0, so it can't turn around. So it has to be continuous and ultimately going to negative infinity. Okay? Same thing at the top, not bounded above, so ultimately it's going there. It could go extraordinarily slowly, but it has to be heading that way. Okay. Do not interpret the last statement to mean that P of T approaches negative infinity as T approaches infinity. We could have that P of T is approaching negative infinity as T approaches some capital T, where capital T greater than 0 is a finite number that depends on the initial condition P of T is equal to P0. Thinking in dynamic terms, P of T could blow up at any time. Thinking graphically, P of T would have a vertical asymptote. T is equal to some capital T, which is greater than 0. Okay. Think sort of blah, blah, blah for here. Okay. Differential equation dy dx equals sin y, the one we did the graph of, is autonomous and has an infinite number of critical points, since has an infinite number of critical points, since sine of y is equal to 0 at y is equal to m pi, n being any integer. Moreover, we know that because the solution y of x that passes through the point say 0, -3 halves. Now remember, this was in the earlier example, example 2, where we had chosen that is equal to -3 1/2. I just 1 1/2. I just happened to draw a curve right through that. Okay, that was what. Okay, it's not going to back up on itself or have anything else. So that would identify which portion. You wouldn't be up here or up here. You're down here, so you're only in region R1. Then you don't worry about the other two. It depends on your initial condition. Okay. All right. Okay, this is just talking about that previous example. I think we already pretty much did it. Let's look at example 5. Solution curves for an autonomous differential equation. Okay. Here we have one that should make a little more sense. It looks more like stuff we've done before. Okay. Here's the differential equation. dy dx, let's go back to black here. Okay, is equal to y minus 1 squared. Okay, now, what would be your critical points there? What values for y would give you first derivative equals 0? 1 and 1 only, it appears. Y is equal to 1. Okay? Single critical point, y is equal to 1. From the phase portrait in the, let's see, oh, that's one coming up. Here's what we've got. Now we have y's on this axis, x on this axis. No more t's in this one, p's or other things like that. Okay, at y is equal to 1, you have a critical point. Okay. Now, from the phase portrait in figure 218, we conclude that a point that a solution y of x is an increasing function in the subregions defined by negative infinity less than y is less than 1. Okay, where does that come from? Okay, well here, dy dx, for this to be an increasing function, dy dx must be greater than 0, right? Well, where is that greater than 0? Everywhere, okay, because it's a squaring function. There's no y you can put in there that will make that negative. There is one that would make it 0, and that's y is equal to 1. We've already identified that. So there's no place this is going to be a decreasing function. It's always going to be increasing. Okay. Now, okay. Sorry about my throat. It's increasing in the subregion negative infinity less than y is less than 1, and it's also increasing in the region 1 less than y is less than infinity. So this is minus infinity less than y less than 1, and here is 1 less than y is less than positive infinity up here. Okay, here's your critical point, y is equal to 1. Okay, what if you had an initial condition, not just this, but you also have the initial condition that y of 0 is equal to y0. Y evaluated at 0 is equal to some value y0, and okay, I lost where it was here. There it is. Okay. Okay. I can't read my writing here. That's supposed to be a y of 0. It's just really ugly. Okay. Yuck. This thing is not picking up. There we go. All right. Y of 0 is some value y0, and we say that's less than 1. Now, why? I'm not real sure why they chose that to be less than 1, but it's okay. A solution y of x is increasing. So y at 0 down here, when I don't know, okay, I don't know why that came from. This y0 is less than 1. Okay. Okay. Yeah. Is it time? Yucca. I'm trying to figure out that it seems like I don't see where the let's just choose the point. I don't see exactly. Well, we'll pick up. We'll pick up there next time. Sorry about that. Okay. They've got two problems here, and I can't tell which one is represented in which figure. I think we've pretty much done the first part of example 5, and we'll begin at the second part of example 5, which is this part. Now y is equal to, and it gives a whole new function. And it just seems to me they jumped a rabbit without going anywhere. So anyway, we'll pick up there next time. And homework exercises here. We almost finished 2-1. Do any of the odds 1 through 1 or 3, either of those, or both. Then do any of the odds 5 through 11. Try number 13, 15, that's isoclines again. Actually, okay. And then any of the odds, we'll do number 19, that's autonomous first order differential equation. And then try any of the odds 21 to 27. Okay, and then we'll pick up and go from there. Okay, sorry about that. I wish we could have ended this a little differently. But the next part I think makes more sense. That one just sort of left hanging and without any real conclusion to it. Let's